Yeah, well, why don't we get started so we don't take too much time from the talk. Thanks everyone for coming in this sort of unusual FAI time, but we have the pleasure of having Erez Karpas here, a visitor from Technion in Israel, which is one that's seen as I think the top institution in Israel, and maybe not everyone would agree with that, but that's conventional wisdom. He did his PhD there as well. And before that was at Ben Gurion. He's also spent time at MIT in Brian Williams' lab, some time at Microsoft. I guess there was a Technion Microsoft collaboration. Yeah. And is now considering coming and spending a sabbatical here at UT Austin starting this summer. So this is both to hear what he's up to because it's of interest, but also for those of you who it touches on close to your research, there may be a lot of opportunities to collaborate over the next year or two. So yeah, with that, welcome and take it away.
Thanks for having me. So Technion likes to say that MIT is like the American Technion. I'm not sure that I agree, but anyway. So I want to tell you about one line of work that we've been pursuing for 7 or 8 years, right? And I say we, I mean this has really been a long-term collaboration with, I think you probably all know Shachaf, right? He was here not that long ago. And we were remote for UNH and Eyal, who's much older than this picture now, but and Andrew Coles from King's College in London. And so let me kind of start with the motivation for this, and then hopefully you'll ask lots of questions. And I'm happy not to finish everything because this is a long talk, right? It's trying to cover like 7 or 8 papers, and I'm happy not to finish it. And then I'm happy to talk about other things as well if you're interested, maybe at our meetings later. So let me start with this motivation, right? And I'll show you a video and I'll explain what you're seeing. So about 7 or 8 years ago, right, I was one of the organizers of this simulated RoboCup Logistics League competition. Right, so RoboCup, right? Obviously, Peter knows it. Started with soccer, but there's a bunch of other competitions now, and this is the Logistics League. It's basically a simulated factory. So you've got these 3 robots moving around between. They're called modular production stations, and what happens is they get orders. So assemble something with a red base, and then a green ring, and a blue ring, and a yellow ring, and then a gray top or whatever, right? And then to complete this order, you have to go through different workstations and assemble the order. So I organized this competition with a guy named Tim Niemuller. He now works at Google X or whatever company they spun out to. And we built this baseline agent the way you would if you were a planning person and you're trying to control a robot, right? You've got a planner, and it comes up with the plan, and then you've got an executive which executes the plan, and then this happened. This is in real time, right? Let me rewind. I'll show you what's happening. Right. So the robots are moving, and then they stop for 10 seconds. Okay. Now, some of you who have maybe built some of these planners that control robots, do you have any idea what's going on here? Took me a while, but here's what's going on. So we had this baseline agent, and every time we had to replan, right? Because this is a dynamic scenario. We've got orders coming in. So whenever a new order comes in, right, for a new kind of product you want at the end, the robots have to replan, right? Our agent has to replan. Now, what happens when you're replanning, right? So in kind of standard planning, you assume that you're going to plan, and then you're going to execute, right? Which is fine. But So maybe I'll just show you this, right? So right, you know this sense, think, act. We've got an agent operating in an environment, right? Executing actions, getting observations. Perfect, right? But when you've got a planner and an executive, right? So planning takes time, maybe 10 seconds. So the planner comes up with a plan, and then the executive is responsible for executing that plan in real time, right? Trying to follow it as much as it can. And if something unexpected happens, then the executive will tell the planner to replan, right? Familiar so far, I hope? Good. So when you're doing temporal planning, right, which is what we were doing because actions take time and can happen in parallel, then you have durative actions. Durative actions take time, which passes in the environment, right? So I plan to drive from, this machine to that machine. It's going to take me 5.7 seconds. Okay. So I know I can start my next action at time, whatever, plus 5.7 seconds. But what we were actually doing is a problem that we called situated planning, right? Because when the robots are doing something, and then a new goal arrives and the robots have to replan, then while the robots are replanning, time actually passes, right? So time passes both in the environment and while the planner is running, right? And that's kind of a big deal if you're on a tight deadline, right? If I have to complete this order in 30 seconds, and now I'm stopping for 10 seconds to plan, now I only have 20 seconds, right? So, one might ask, well, why are we stopping, right? Why not continue executing the old plan while we're coming up with the new plan, right? What's the problem with that? What's the initial state, right? If I started planning from this state, right, the state that occurred, the state that the world was at while replanning was triggered, right? But then I continue executing actions, right? Then I'm going to start executing my new plan from this state. But my plan is valid from that state. Why is it going to work, right? So, right, so I was kind of looking at this going on, and I figured, that's weird. Let's try to formalize this, and then we came up with this formulation for situated planning, which I will show you a bit more formally in a minute. But then we realized something else, right? Situated planning is still making a big commitment, right? Or has a big constraint, which is it has to have a complete plan before actions start executing, right? And there are certain situations where we want to execute an action even before we have a complete plan, right? For those of you who work on reinforcement learning, that's kind of natural. For us, it was kind of surprising, right? But we ended up defining this problem we call concurrent planning and execution, in which we actually merge a planner and an executive into something that can decide to execute an action, dispatch an action, even before it has a complete plan. And of course, there's risks and advantages to doing that. Okay, so why is this important? So, obviously, if you don't have any, deadlines, any external temporal constraints, it's not. Right? Just do offline planning and then execute a plan will always work, right? But if you have deadlines, right? If I have 10 seconds to achieve my goal, then taking planning time into account is critical. Because if you take T time to plan, then you have, 10 minus T seconds to execute, right? So if you think about planning to catch a bus at 10:35, right? You better leave here at 10:32 to make it to the bus stop on time. And if you don't have that plan ready to execute, or at least the first action ready to execute at 10:32, you're going to miss the bus, right? But then you might have a different possible plan which catches the bus at 10:55 or whatever, right? And then you have more time for that. So you have to trade off planning time and deadlines and manage all of that. So the thing we try to optimize, even though we don't actually do that, is what we call goal achievement time, which is the planning time plus the make span. And note that it's infinite if you don't actually achieve the goal, right? So you want to achieve the goal. Okay, so before I start getting more formal, Questions? Anything? Okay. So, how do we formalize this? So this is kind of the basic problem statement for offline temporal planning, right? Standard temporal planning, PDDL 2.1 or whatever you want. So the problem is given by F, which is a set of Boolean facts that describe the state of the world, such as Boolean variables. A is a set of derivative actions, and if you're not familiar with derivative actions, the details are not very important, right? But you've got kind of a start snap action and an end snap action, which have preconditions and effects, and you've also got an invariant condition that has to hold throughout the execution of the action. And then, of course, the action also has a duration. You've got your initial state, which is which variables are true in the beginning. You've got a set of timed initial literals, or tils, right, which basically say at time t, literal L will occur, so some fact will become true or false. And this is basically, think of this as deadlines, right? So these model changes that will occur in the world in the future, right? So we know this bus will come at 10:35, and this bus will come at 10:55, and this bus will come at 11:05, whatever, right? So you can model these as tils, right? And without this, it's really meaningless. But you can just think of this as deadlines if you want, it's easier. And then you've got, of course, the goal, right, which is what you want to hold at the end. So this is the input, right, and what we want to get is a plan or a schedule, right, which is a set of tuples that say you start action A at time t with a duration of d, right? So this basically just gives you a schedule. And you can have actions going on in parallel here, okay? If you really want to get technical, you can't have two events happening at the exact same time. You need to have epsilon separation, but it's not really interesting or important.
And you measure the time that the goal needs to be achieved by also in t?
Yeah, so basically the time when the plan completes is the maximum over t plus d, and we want the goal to hold at that time, right? And then the make span of the plan is that. Yes.
But that's like, so in capital T, which is the time, the initial literals, that's the things
Oh.
say when things happen.
Yeah,
Is
yeah,
that
yeah.
also, you say like you've achieved your goal if it happens before a time and you haven't achieved it
Um,
after, or is there some, because I don't see otherwise where you say the deadline for achieving the goal.
So usually what this does is it would say at time deadline, you delete some fact, and that fact is a precondition for everything else, right? So if you haven't achieved your goal by then, you never will.
Okay.
That's one way to model a deadline, right? But this is more general. But that's a good question. I don't think it ever occurred. But generally, we don't care about the till so much. We just care about the plan. But the plan does have to include the tills which we use, right? So it's slightly trickier. Okay, so then the plan is valid. Again, without going into the details, if applying each action at designated start time achieves the goal G at the end, right? Okay, so this is standard offline temporal planning. So what do we need to change to formalize the problem of situated planning, right? Which is kind of time passes while you're planning. Well, that's the only thing you need to change. You just need to add this line at the end. It says that if it took you X time to plan, then the minimum start time for every action is more than X. Right? So this is basically saying at time 7, I can't say that I started action at time 5, obviously, right? So very, very small change in the definition, right? But as you'll see in about 2 minutes, it's a huge change in how we actually have to solve the problem, okay? Actually, it might be more than 2 minutes, but you'll see it at the end. Okay, and then we can also define concurrent planning and execution, right? And in concurrent planning and execution, the output, right? We don't look at when we get the complete plan, but we look at the time we output each of these tuples, right? Because we can output them at different times, and we say that if you output ATD, right? So kind of start executing action A at time t, then you have to execute it in the future, right? So if you say this at time x, then the start time has to be greater than x, right? So I can say, at time 2, I can say start executing this at time 3, and then at time 7, I can say start executing that at time 9, right? And usually it's going to be t equals x, right? Because there's no point in committing to something too early, but that's if we were completely rational, and as you'll see, we haven't gotten there yet. Okay. So here's an example. So now I remember that the first paper was in ICAPS 2018, because the example is about getting to Delft, right? So suppose you have this, die-hard type of planning problem, right? So you have to solve a Rubik's Cube and then get on a train from Amsterdam Airport to Delft by 8, okay? And so your flight lands at 6 in the morning, and then you've got 3 options, right? You can take train 1, which leaves at 6:30, arrives at 7:15. You can take train 2, which leaves at 7:30 and arrives at 8:15. Or you can take a taxi at any time, and it takes 35 minutes. But this is more expensive, so we kind of prefer not to do that. So if you knew the initial configuration of the Rubik's Cube before you get on the plane, right, we would have an offline planning problem, right? Because then we could, plan how to solve the Rubik's Cube on the plane, and then we land, execute the moves, solve the Rubik's Cube, get on the train, and we're done, right? But what happens if the initial state of the Rubik's Cube is revealed only when we land, right? So then at 6 a.m., we have to start planning how do we solve this Rubik's Cube and then get to Delft, okay? So this is our, I don't want to call it motivating example, but it is a running example. Okay, so the way we typically solve planning problems is via search, okay? Tree search, just because it's easier to draw. So when we're talking about offline planning, right, then we can kind of look at the time we're going to start executing, right, and it's going to be 0, right? And then we expand some node, okay, so we're still going to start at time 0, we expand another node, and expand another node, and we find a plan, and then we start executing at time 0, right? Obviously it doesn't make much sense, but that's offline planning. Now, if we're doing situated planning, then what happens is that nodes can expire during search, okay? So think of, the node which represents getting on the 6:30 train, right? Or whatever, yeah. So at 6:31, that node is expired, right? It's no longer applicable. You can't use it in any plan. So if you visualize this, right? So you start at time 0, and we measure time by expansions here. So it's not, perfectly accurate, but it's much easier. So after one expansion, right, let's say an expansion takes 1 second, then the time is 1. And after another expansion, the time is 2. And now this node is yellow because it's kind of close to its deadline, right? And then I do another expansion, and at time 3, this node is expired, right? This node is no longer available to us, right? This is like the 6:30 train, and if an expansion takes 10 minutes, okay, then after 3 expansions, this is no longer applicable, okay? And finally, in concurrent planning and execution, what you can do is you can commit to an action, right? And that does 2 things, right? On the positive side, it buys you time because you've advanced along one plan, right? So you relax your time pressure for that plan, right? But on the other hand, you prune the rest of the search tree because once I've committed to, action 1, I can no longer apply action 2, right, from the root. So this is a big trade-off, right? So time equals 1, right? You're in this state, and then time equals 2. We've got this node, and we see, okay, the time pressure here is tight, right? So we can decide to commit to this first action, right? So at time equals 3, this node is not expired because we've committed to this green action, right? So we've relieved some of the time pressure, But on the other hand, this subtree is expired. It's no longer available to us, right? So that's what we have to deal with. Okay. So this is the problem that we're trying to solve. And now I'm going to go into some of the details on what the search space looks like. So basically, it's just a search over sequences of starts and ends of actions with some modifications, some temporal constraints, and things like that. I'm going to talk about the heuristic. We really haven't done anything or almost anything with the heuristic, so we just use kind of the standard temporal relaxed planning graph. I'm going to talk about the temporal reasoning we need to do in order to decide about the deadline and things like that. So it's a modified version of the simple temporal network that POP-F, one of the popular temporal planners, uses, modified to account for the current time, right? And then I'm mostly going to talk about the meta-reasoning that we need to do. So why do we need to do meta-reasoning, right? It's because in kind of standard offline search, right, offline planning, we really care about minimizing the number of expanded nodes or minimizing search time or optimizing plan cost or something like that. But we have usually one objective, right? Here we need to worry about two things, right? We need to worry for each node, right? We need to worry about how long is it going to take me to find a plan under that node, right? We call this the remaining search time, and the deadline for that node, right? So what is the latest time I can start executing an action from that node? And we have to consider both of these together, right? So we turn to meta-reasoning to do this, right? And if you know Shachaf, then this is probably familiar to you. Okay, so let's start with the basics, right? Which is kind of basically the first three. So how do you make a temporal planner aware of passing time? Okay. So I don't know how familiar you are with temporal planning and STNs. Does this look familiar to anyone here? No. Okay. Okay, this might take longer than I thought. All right. So a simple temporal network is a formalism introduced by Rena Dechter and Yuda Pearl in '91. Basically, it's a very simple type of CSP, constraint satisfaction problem, right? You've got time points, right? So when do we start action one? When do we end action one? When do we start action two? When do we end action two, etc., right? And a set of temporal constraints between them, right? So for example, the time between this time point and this time point needs to be between 0 and 90, okay? And solving an STN can be done in polynomial time, right? Because it's basically just a bunch of linear constraints between continuous variables, right? So it's an LP, you can do it very efficiently. And standard temporal planners, what they do is they take what we call a plan skeleton, so a sequence of starts and ends of actions with the temporal constraints that come from the ordering and the durations, and they turn this into an STN, and then they solve this STN, right? And the standard way to do this is to say, okay, I have a 0 time point, which is when the plan is going to start executing, right? And then I've got my actions, right? So in this example, we've got action 1, which takes between 2 and 3, and action 2, which takes between 4 and 7, and we've got a deadline on action 1 needs to end before time 90. So you can see that this STN is solvable and very simple. Now, to address time-aware planning, let me just skip to this. What we do is we introduce 2 new time points. So we separate the starting time, right, TS, into planning start and execution start, right? So basically we're saying we're going to start planning now, right? And we started planning at time TPS, right? And the deadlines are now relative to when planning started, right? Because once we start planning, time starts passing. So this 90 time units deadline is now relative to planning start. And then all of the actions have to occur after execution start, okay? And then we've got T now, right? T now is when we are now, right? So we've already spent 2 time units planning, right? And then we've got some unknown amount of time until we finish planning and start executing, right? So this is for the situated planning case.
Because this doesn't allow for interleaving planning and.
No, we'll get there, but this is like the first paper. So we're not there yet, but we will get there. So we've got this unknown duration here, which I'm gonna get to in a second, but then everything else is just a regular STN. Okay. So the first thing we can do,
Question?
yeah,
The unknown duration is just the planning time?
this is the remaining planning time, yes.
The remaining, okay.
Yes. So this is the total planning time, this is the remaining planning time. So if we treat this as 0, right, then what we can do is we can prune search nodes where this STN is inconsistent, right? So if we put 0 infinity here, right? So basically planning can end any time it wants, and if this is still infeasible, so there's no solution which satisfies all of the temporal constraints, that basically means we've missed the bus. It's too late. We can prune this node. It's not going to lead to a solution, right? So this, this red thing that I showed you here, right? This really means that this STN that I showed you is inconsistent, right? So this is how we actually figure this out. So we don't have to wait until the end. We can figure this out early enough. Okay. And these are guaranteed never to lead to a feasible solution, right? So we can prune them safely. And I think this is going to be the last time that there's anything I show you here that's actually safe to do. Okay, so here's an example of this, right? So this is the running example, and let's look at the STN for taking train 1, okay? So planning start is going to be at 6 in the morning, and let's suppose that it took us 31 minutes to solve the Rubik's Cube, okay? And then execution is going to start at some point, right? And then we want to board train 1, so we're looking at the STN for one possible plan. And then we've got a constraint that says that we have to board the train at time 6:30, right? So this is the 30 here. But if you're familiar with STNs, you'll see this is inconsistent, right? Because this takes at least 31 minutes, but this has to happen at least 30 minutes, right? So this is inconsistent. Basically, this is a way of capturing that we've missed the train, okay? So we can just prune this node from the search tree. Okay, so what, was there a question on Zoom?
No.
Okay,
No.
all right. So what happens if it's not too late now, right? But we estimate that the search is going to complete too late. So we're not sure it's too late now, but we think it's going to be too late once we finish planning. So how do we do that? First, we have to estimate the remaining planning time, right? Then we can incorporate this estimate of remaining planning time into the STN. But then, of course, we can't safely prune this, right? Because we only estimated the remaining search time, right? So we're not sure. So what we do is we use a dual queue mechanism, a dual open list, right? So we maintain 2 open lists. One of them only contains the search nodes where the STN is consistent, right? So when we think we're going to be on time. And the other one contains all of the nodes, even those where we think it's going to be too late, but we're not sure, okay? This is a standard thing that Fast Downward did already 20 years ago. I mean, with different heuristics, right? This is slightly different. So this guarantees completeness, right? But still gives priority to the nodes where we think it's not gonna be too late. Okay. And then, of course, you can also use metareasoning, which I will go into a bit later. Okay. So how do we estimate a remaining search time? So we So we use a technique that Wheeler Rummel developed for his work on deadline-aware planning. So what we do is this. We look at something we call the expansion delay. So the expansion delay of a node is the number of expansions between when a node was first generated and when that node was expanded. Right? So this is essentially the number of nodes in a search layer. Right? Because when you generate a node on layer I, right, and then you've done 1,000 expansions, right, and then you expand that node, go into layer I plus 1 at 3,000 expansions, right? So you've got about 2,000 nodes in that layer, right? And we use an average over a sliding window to get a number for that. Okay, so this gives us the average nodes per layer. Then to translate that into time, we just measure the expansion rate, right? Which is why we basically measure time by expansions, right? We just need to measure how long does it take me on average to expand a node. So the expansion delay gives me the number of expansions for one layer, and then of course the question is how many layers do I need to go to reach the goal, right? And fortunately we have a heuristic, so we look at the heuristic distance to go, right? So we don't care about the cost or the make span of the heuristic, we just care about the number of actions that the heuristic accounts for, and we use a relaxed plan, so it's really easy to get, okay? So our estimate of remaining search time is basically the expansion delay times the distance, right? So how many layers I need to go times how many expansions per layer, and then to translate that into time, we just divide it by the expansion rate, right? So fairly simple estimator. Is it accurate? No. Is it useful? Yeah, a little bit, slightly. It's the only one we've got, so we use it. But this is definitely an area we can improve on. Okay. Yeah.
Could you explain again the expansion delay? Why does it affect the remaining search time?
So the expansion delay measures how many nodes I need to expand in order to advance one layer in the search tree, right? So if it takes 1,000 expansions to advance one layer, right, and I need one layer is one action in the relaxed plan, right? And if I think it's going to take me 10 actions to reach the goal, right, then I need to advance 10 layers. So 10 layers times 1,000 expansions per layer gives me 10,000 expansions, right? And then I can translate that into time. Now, we know that the expansion delay actually tends to increase, right? Because the search tree actually gets, if it's a tree and it's exponential, right, then this is worthless. But because we have a heuristic guiding our search, and because we're not really expanding the full tree, and because we've got duplicates and whatever, and mostly because we're using a sliding window, it works, it does something. But yeah, there's definitely better ways to improve. I actually advised a student to use an LSTM to estimate the remaining search time, and that was much more accurate. But then, of course, you don't want to, run inference on an LSTM every node you expand, right? So we're not actually using that, but it is an interesting way to go. Okay, yeah.
Do you assume the heuristics to be admissible, or do you have any assumptions about the heuristic here? So
No, we don't assume anything. Actually, we know that the heuristic we're using is not admissible, although it does tend to be optimistic. But we don't need admissibility for anything here.
I see, but would that affect the quality of your estimated remaining time?
Actually, for this, I'd rather not have an admissible heuristic. I'd rather have an accurate heuristic, even if it's sometimes wrong, on the other side. What I care about is accuracy, not admissibility, because I'm not trying to guarantee anything about solution quality or anything like that.
Okay. Oh, so basically the heuristics don't affect the accuracy of your estimated time.
I mean, they affect the accuracy, but okay. I'm jumping slightly ahead here, right? What we're gonna do when we get to meta-reasoning is we're gonna try to maximize the probability of finding a timely solution. We don't care about the quality of the solution, right? We just care about finding a solution on time. And even that is not guaranteed in this setting, right? So it's a lot less forgiving than offline planning, where if there's a solution, you can always find it, right? In situated planning and in concurrent planning and execution, you can't even guarantee completeness, right? Because there might be a solution, but you've just spent too long searching somewhere else that it's now too late to execute the solution which was there when you started, right? So if you can't guarantee completeness, then we're not even, close to talking about optimality.
Okay. Mhm.
Okay, yeah.
Just to get the intuition right, so this estimation on remaining search time, so is run, like, how often is this being run?
This is for every node,
For
because
every
we're
node?
already computing the heuristic, right? So it's just a matter of maintaining this running average over expansion delay, which is basically free, and expansion rate, which is also free, right? So getting this is basically the same cost as computing the heuristic, which we're doing anyway.
So so for every node, if you decide to expand, you're taking this estimate of how
Yeah.
long you think you're still gonna,
Yeah.
you're gonna search
Right.
for, right? So that's
Yes.
why an LSTM would be problematic, because you would have to run.
Yeah, if we're using an LSTM, yeah, we need to do something else, yeah. So if we were to integrate an LSTM into this, we would probably, run it every 1,000 expansions and then kind of try to do this dynamic propagation of the search time from the last inference of the LSTM or something like that. But I don't know. I've got some very rough ideas, but
Does it ever matter, like, how long, do you ever have to account for how long this calculation takes?
no. So I mean, the most expensive thing here is the heuristic,
Okay.
which takes basically polynomial time in the problem size, and everything else is basically constant time. So we don't worry about that.
So in the motivating problem of the RoboCup logistics lead, what are the timescales involved? Like, is planning time really significant? Take seconds compared to the action? I mean,
So
most of the planning in that context should be like milliseconds, right?
Well, yeah, if you're winning the competition, then planning takes milliseconds, yes.
So does like in that, what's the example where the planning time is actually significant?
So I'll give you a very good example of this. Actually saw an autonomous Waymo driving around yesterday, right? So imagine you have an autonomous car, and maybe it's planning a really long drive here, I don't know, from here to Houston, whatever, right?
That comes up on my phone like in like milliseconds too.
Well, so there's special heuristics for path planning, right? But I think autonomous vehicles plan something even more detailed. So imagine you're this autonomous vehicle, and let's say it takes you 5 seconds to plan, right? Just for the sake of the example. And then you've got a truck backing towards you. It's gonna hit you in 4 seconds. Right? Maybe I start driving now, before I know how to get, whatever off the freeway to Houston, right? I should start driving now and finish planning my trip later, right? So this is my canonical example.
Yeah, I guess the thing I'm quibbling with is the 5 seconds part. Like, does it really take 5 seconds to plan it?
Okay, so in the RoboCup Logistics League, the competition takes 20 minutes, and we use the PDDL planner. So we set the time limit for planning at 10 seconds, and this was not too far-fetched, right? Sometimes you finish in 2 seconds, sometimes you need all 10 seconds. And it also really depends on the complexity of the problem and on your CPU speed, right? So at the end, I'll show you some results we have for concurrent planning and execution, where we look at the difference in performance as a function of the number of expansions per second you can do, right? And if you think about a Mars rover, right? So one of the examples we think about is opportunistic science, right? So you've got these Mars rovers, right? And they're driving around, and don't ask me why, but they like to take pictures of dust devils. I don't know, scientists found this very interesting for some reason, I don't know. So you're driving around, from rock 1 to rock 2, right? And suddenly there's a dust devil. And if you want to take a picture of the dust devil, you have to stop, you have to take out your camera, you have to, whatever, it takes time, right? So you have to figure out very, very quickly, also on a very slow CPU, because these spaceborne CPUs are like an order of magnitude slower and single-threaded, and don't have GPUs. Should you stop and take advantage of this opportunity, right, and collect the utility that's going to get you, or and possibly, right, you don't know that. You have to figure out whether that's going to cause you to miss your goal, right, or maybe even miss your opportunity to communicate with Earth, or miss your opportunity to charge, or whatever, right? So you have to figure all of this out very, very quickly before you lose the opportunity, right? So there are examples of this. Now I will say that for RCLL, the winning entry in the competition is really something based on the Clift's executive, which is kind of logic-based rules which figure out what to do in milliseconds, because the planning part of RCLL is trivial. The only interesting part is how you handle 2 orders concurrently. Right? Because if you've got 3 robots and 2 or 3 orders going on at the same time, you know which actions you need to do for each order, but you have to figure out in which order to execute them in order to meet all the deadlines.
So that's more of a scheduling problem.
It is more of a scheduling problem, yes. So in terms of planning, it's really planning plus scheduling together. The problem is, we don't know how to tell our planner that the planning part is easy. So it's doing the planning and scheduling together, which is making things harder than they need to be. Yes, that's very true.
So since I'm contributing to slowing you down, I should probably also just do a time check. We've got about 15 minutes.
Yeah, that's fine.
Can I ask
Yes.
one quick question? So the only one unknown quantity is the planning time. What about execution time?
So we know the durations of all the actions. So if we have a, so we'll get there. What's unknown? So this is one unknown, right? Planning time. The other unknown is the deadline. It's not the execution time, but it's what is the latest time I can start executing in order to be on time. I will get to that in a second. Okay. So here's an example. So the same example for train 1, except we've been planning for 5 minutes, but we think it's going to take us 30 more minutes to find a plan, right? So we get this STN now, right? So this is 5 and this is 30. And again, this is inconsistent, right? But now we can't prune this, so we only put this on the kind of bad open list. Okay. So now let's get to the deadline, right? So far we only looked at the length of the relaxed plan, but we can actually look at the contents of the relaxed plan and compute what we call the slack of the relaxed plan, or the latest start time or the deadline, right? And this is just how much we can delay the relaxed plan while remaining consistent with the tills, right? So what I didn't show you is that the tills, right, they're really here. Right? So this is the train 2. And the slack really strengthens the constraint between planning start and execution start. So it's telling us this plan can be started no later than 7 a.m. or whatever, right? And of course, this is also not admissible because we're basing this on a relaxed plan and not on a real plan. So if we had a real plan, we can compute this exactly. Because it's a relaxed plan, then this slack might be too optimistic or too pessimistic. We don't know. So if you look at the STN for taking train 2, right? So we board train 2 at 7:30, which is fine, right? But the relaxed plan contains that we're going to arrive at 8:15. And 8:15 is too late, right? So again, this is a trivial inference, right? But you can generalize this to more complicated temporal reasoning, and it will do the same. So we're going to figure out that train 2 is too late, and we're not going to prune it because this is a relaxed plan, right? So we're only going to put it on the bad open list. Okay. So now let's get to the meta-reasoning part. So here's where it gets tricky, right? And I kind of showed you this in the beginning, but I want to come back to this point. So in offline search and offline planning, there's a basic assumption, which is that the search tree remains the same. And we want to find a plan as quickly as possible in this constant search tree, right? Except with situated planning or with concurrent planning execution, this is not true, right? Because nodes expire, right? So I mean, the way I like to think of it is you're searching through a tree, but the tree is on fire, and you don't know the burn rate of each of the tree's branches, right? And you kind of want to find your way to one of the branches before it burns. So what we want to do, right? We don't want to minimize search time. We want to maximize the probability of finding a timely solution. And that involves reasoning over search time and deadlines together. And we don't know either of them completely, right? So we turn to meta-reasoning. And I will say, before we started working with Shachaf and Eyal, we really had no idea about this meta-reasoning stuff, but then we started writing a bunch of papers about abstract models for meta-reasoning, and then we incorporated them into the planner, and it was a whole lot of fun. So meta-reasoning is the process of thinking about what to think about, right? So formally, we define a set of computational actions, and then we want to find a policy that tells us which computational actions to perform, right? So what we're going to do is this. We're going to define the full meta-reasoning problem. We're going to prove that it's too difficult. We're going to formalize a simpler problem. We're going to show that it's too difficult. And then we're going to come up with some greedy scheme for solving the simpler problem. And then we're going to profit. So what's the full meta-reasoning problem? Basically, think of this. You have an MDP. Each state in the MDP is a state of the search tree that we've expanded so far, right? And actions correspond to deciding which node to expand, right? And that gives you a probability distribution over the next possible state of the search tree, right? Don't even think about formalizing this, right? It's terrible, right? So what we did instead is we formalized a simpler problem where instead of thinking of a search tree, we think of n different computational processes, right? And you can think of kind of each node on the open list as a process, right? And then each process is characterized by a distribution on the remaining search time, right? We don't know the remaining search time, but we can estimate it and we can fit some distribution around that, and some distribution on the deadline, right? And what we want to do is allocate the next unit of computational time to each of these processes, right? And with these MIE and DI, we can characterize exactly the probability of success of a policy, okay? I won't go into too much detail here, but basically, if you look at a time horizon of t, then you've got n plus 1 to the power of t possible states, and you can derive the transition probabilities from these MI and DI, and this is really Shachaf, right? So we proved that this is NP hard by reduction from knapsack. I think you've probably seen the same thing. So what do we do? Well, apparently you can restrict yourself to contiguous linear policies, right? So contiguous means you allocate search time to some process, and then once you're done, you don't go back to that process anymore. And linear means that your action at time t doesn't depend on the results of the previous action, right? So instead of finding this branching policy, you can just kind of say, I'm going to allocate 5 time units to process 1, then 7 to process 2, then 3 to process 4, okay? And we can compute the probability of success for each of these, and apparently we can find the optimal policy here in polynomial time in end and in t. So it's not really polynomial, right? It's pseudo-polynomial because it's polynomial in the time. So, that's progress, but it's still far too slow to do this for every node we expand, right? So instead, what we do is we came up with this greedy scheme, which we call delay damage aware, okay? So again, I don't want to go into too much detail here. The most important thing I want to show you is we define this thing called LPF, the log probability of failure, right? And we can compute this from MI and DI, right? So this says if I allocate T time units to process I beginning at time TB, what is the probability of failure, right? We can compute that, right? And then we can define something called the most effective computation time based on this. And then we can look at kind of what is the damage if we start now versus if we delay this and start TU time units later. And this gives us something called Q, which is basically our estimate of the utility, right? So we do this and we sort our open list based on this Q value. Of course, we have to tune this gamma hyperparameter and this TU hyperparameter and a bunch of other hyperparameters I haven't talked about. And it works, right? Except this is an abstract metareasoning problem and we want to integrate this with the planner, right? So how do we do that? So there's two things we need to do, right? We need to estimate our distributions, DI and MI, right? I showed you how we estimate the remaining search time, which is not a distribution, right? It's just a number. And I showed you how we estimate the deadline, right? Again, a number, not a distribution. And then, of course, we need to integrate this greedy scheme into the search. So I'll start with the simple things. For the deadline, we just assume that the deadline is known. So basically, we take the estimate that I told you about before from the temporal rack spanning graph, and we say, with probability 1, this is the deadline. So after this, it's going to be 1. Before this, it's going to be 0. It's not accurate, but it's the best we know how to do. For remaining search time, we do something that's slightly more sophisticated. So we look at the one-step error, right? So think of a heuristic search, and that's estimating the distance to go, right? So only care about the number of actions. So suppose the heuristic says that this node is distance 5 from the goal, right? Then it's got 2 children. This one says it's 5 away, this one says it's 3 away. Is the heuristic correct here? So it's definitely making a mistake, right? Because, so this is the best child of this node, right? And what we expect is that if we advance 1 step towards the best child, that the heuristic distance to go estimate will decrease by 1, right? So we expect this to happen, that the distance between the best child of S minus the distance of S is going to be 1, right? And here it decreased by 2. So we have an error, 1-step error of 1, right? What we do is we keep track of the distribution of 1-step errors, right? Just a histogram of these 1-step errors over our search, right? Because we can measure this as soon as we expand the node, right? And then we denote this distribution by OD. So this gives us the heuristic error in 1 step. What we care about is the heuristic error for the entire plan, right? So we just convolve this 1-step error with itself D times, right? Where D is our estimated remaining search time, right? And that gives us basically an error distribution on the heuristic distance to go, right? And then to translate that into time, we just do same thing we did before. We multiply this by the expansion rate divided by the expansion delay divided by the expansion rate. So that translates from heuristic distance to time, okay? So that gives us the MI distribution. Okay, so how do we integrate this greedy scheme into the search? And I think I'm going to end here and not go into concurrent planning and execution. So we've got a bunch of problems, right? So the problem is that this Q value changes, right? because it depends on this one-step error distribution and the expansion delay, and these change over time. So we recompute Q for every node in the open list every, say, 100 expansions. Our meta-reasoning assumes we allocate TU time units to the chosen process instead of one, so we actually just do that. So we're not doing a standard search anymore, we're just kind of allocating a chunk of expansions to a subtree at a time. Think about 100 expansions at a time instead of one. We need some statistics which we don't have in the beginning, right? And if you just use the statistics after one expansion, you might just go off in a completely wrong direction. So we only start using this after some minimum number of expansions, right? And then there might be lots of ties, right? If you don't have any deadlines, so we break ties just by the heuristic. So a lot of kind of simple things that you need to think about. We didn't think of them in the beginning, which is why it didn't work in the beginning, but now it does. Okay. And then, of course, this was situated planning. If you think about concurrent planning and execution, committing to an action is a very strong decision, right? Because, so kind of think about, allocating 100 expansions to some subtree at a small cost of being wrong, right? Executing an action, if you're wrong, has a huge cost, right? Because you've committed, you've executed an action, you've denied yourself half the search tree, right? And what we did, in the beginning didn't really account for that, so we had to kind of introduce this measurement model which accounts for possible errors. So we basically don't commit to an action unless we've expanded some minimum amount of nodes in the subtree of that action. So just to kind of show you some results. So this is the CPU speed measured in expansions per second, right? The blue line is what you do when you just do situated planning. And then this is the concurrent planning and execution with different hyperparameters, with 1 robot, 2 robots, and 3 robots in RCLL, right? So if you look at this, there's a huge gap in performance here. Okay. So skipped some of the important things, but not too much. So basically, I showed you that there's a simple and principled problem formulation which combines planning and execution. And even though the problem formulation is simple, the solution is not, right? And meta-reasoning does help here. Thank you.
So we asked a bunch of questions during the talk, but maybe time for 1 or 2 now, and then we should wrap up soon because there's a faculty candidate talk starting. So,
Yep.
Yeah.
So why not just do something like for the whole situated problem? Why not do something just like upper bound the amount of time it takes you to compute a plan? Select some plan that's good enough to execute and start planning from the state you'll end at the upper bound time. Like as sort of a baseline person, I didn't hear you really discuss that kind of thing. I think it fits into this framework.
So if I was able to select a plan to begin with, I wouldn't need to do any of this, right? Because if I have a plan, then I have a plan, right? I only care about maximizing the probability of finding a plan on time, right? So if I was able to come up with, even with a bad plan, in 0 time, my problem is solved. This is not the problem that we're solving. We're solving the problem of how do we find a plan, even the kind of the first bad plan, early enough to execute that, right? But you're right that if we're considering kind of improving plan quality and we had a bad plan to begin with, yes, we definitely can do something like that. We have a paper about meta-reasoning with action costs. We haven't incorporated that into a planner yet, but that's on our to-do list.
Have you continued to explore that area of estimating like time left to plan?
A little bit, yeah.
Because like I had an idea, like what if like I do a lot of work with like planning and uncertainty, and sometimes we augment the state space with like some measure of uncertainty, let's say covariance of the state. And I'm like, okay, what if you augment the state space with like time for planning, right? Then you have to come up with some dynamical system for how you expect your time to plan to change over time. But that's an idea I had, and I was wondering if that's like a direction you also explored.
We tried doing something like that. It's slightly more complicated, but yeah, we're still working on that, right? We don't have anything definitive yet, but it's an interesting direction for sure. Yeah.
So this does not require gathering the training data.
This is you would call it zero shot. If we had this, kind of training data from similar problems, then we can bootstrap our MI and DI estimates based on that for sure.
So your heuristic estimates are inaccurate in the beginning, but it gets more accurate.
Hopefully.
Okay.
Okay. Thank you.